Hi, welcome back to LeetCode. So in this video, I am going to discuss LeetCode problem 3608. Minimum time for k connected component. So you are given an integer n and an undirected graph with n nodes leveled from 0 to n minus 1. So there will be node from 0 to n minus 1. Okay. This is represented by a 2D array edges. So here edges I indicates that UI, VI and time. So it indicates an undirected edge between nodes UI and VI that can be removed at time I. Okay. So you are also given an integer k. Initially, the graph may be connected or disconnected. Your task is to find the minimum time t such that after removing all edges with time less than equal to t, the graph contains at least k connected components. So we have to find out the minimum t. Okay. So what is connected component? So means if this node is actually connected, so these three actually nodes are actually connected, right? So this is actually one component. Suppose there are actually 5 nodes. Okay, n is equal to 5. So this. Okay, these 5 nodes. Now suppose the edges, I actually added the edges. So suppose this actually the edges, another edges suppose here in between these two nodes. So here in this graph, how many actually components are there? So this is actually one component, right? This is actually component 1 and this is actually another component, right? Component means the nodes that are connected. Okay, so one component will contain all the nodes that actually directly or indirectly connected. Here actually you can see these 3 nodes actually directly or indirectly connected. Similarly, these 2 nodes are actually connected directly or indirectly, correct? So there are 2 components for this graph, right? We can say that. So what actually we have to do? We have to find out the time t such that minimum time t such that after removing all the edges that will be removed at time, they mention time I. Suppose for this example, let's see this example. Suppose I want to find out the one t such that after this time we actually have at least k components, right? So that means suppose I want to find out that after time t is equal to 5, how many components we will have. Okay, so this is actually the initial graph. This is the initial graph. So t is equal to 5. I have also mentioned that after the time t, that this edge will be removed. Okay, so t is equal to 5. So again draw the graph. So I actually have 6 nodes. Okay, so let's see this edge here to t is equal to 5. T is equal to 5. So this edge will be present in the modified graph at t is equal to 5. No, because it will be removed at the time 1. So it will not be present. Next, this edge, it will be present in the modified graph. No, because it will be removed at 2. 2 is less than 5, so it will be removed before that. Now, this edge can be present at the modified graph. No, because time is 5 and also we are actually creating the graph at the time is equal to 5. So it will be removed, right? They mention that the time less than equal to t, so it will be removed. So that's why here actually 5 also be removed. Now this edge will it be present in the modified graph? No, because the time is 3, but our honestly creating the graph 5 at the time 5, so it will be removed. Next, this edge, will it be present? Yes, because the time actually is 10. It will be removed at the time 10, but we are actually currently at time 5, so it will be present. So what is the edge? Edge will be this, right? Now how many components I actually have in the graph, in this graph? So this is one component. Any other node is present part of this component? No, because there is no edge from this node. So next node is this node. Here actually it is component number 2. You can also do the numbering also. So any other node is part of this current component 2? No. So next is suppose this 3, component number 3. So this actually one component. Any other node is a part of this current component number 3? No. So next is suppose this is the component number 4. So Okay, so we have to identify all the nodes actually part of the current component. Yes, I will traverse this edge. So this node will be part of the current component. So it will be also part of component number 4. Next, no other nodes left. Next is this node actually still actually part of not a part of any group, any component, right? So I will actually give any component number 5. Next component number. So any other node part of this current component 5? No, because there is no outgoing edge. So actually, how many actually components are actually here? 1, 2, 3, 4, 5. So 5 actually components are here. Suppose k is equal to 3. I want to know that on which time, minimum time, I can create actually k at least k number of components. So here actually 5 components I can actually create after t is equal to 5, right? So this is actually the steps I actually follow. So what is the brute force approach we can actually think? Brute force approach. So first of all, we have to identify minimum time, right? Minimum time. So what will be our time will start? It will start from 0 to it will go up to 10 to the power 9. Why 10 to the power 9? They mention that the t can go up to the maximum time it can take 10 to the power 9, correct? So that's why our t can start from 0 and it can go up to 10 to the power 9. Now what will do? For each current t, I will check that how many actually component it can creates, right? So how many components actually we can actually create? How can you do that? So this is another problem. So to create a component or count how many components are there in the graph. So that's why what I have to do? Next step, first of all, create the modified graph. Modified graph means, so consider only the edges that actually time is greater than t. That edges will be only considered in the graph. So then actually I will create a graph. Okay, something like this. Okay. Now what I will do? I will actually count the components. So we all have solved the problems that count the number of components in the graph, right? So what actually we do actually ultimately we will take one visited vector. Okay, and also I will take one component variable that actually initially that there is 0. This actually current component will be 0 component number. It indicates the component number. Now I will start the visiting from suppose any random because this actually undirected. So I can start from here. I can start from here anywhere. So now what will initially all are actually false because I have not visited any node till now. So initially all are actually false. Suppose I start from node 0 or this node. So what I will do? I will mark this. Suppose I will mark this as true because this node is visited. Next, I will go to the adjacent of this node. So I will visit this. Suppose actually this node. So I will mark this as true. Again, this actually the adjacent of this. Suppose actually initially false. Now I will mark this as true. Got it? So there is no adjacent node for this node that actually not visited till yet. So this will be actually again the adjacent for that this node. But this actually I have already visited that node. So that this is not needed again. Now I will go to the again. I will come to this node. Okay, this is not yet visited. So I will mark this as true. Okay. So initially I will visit the first component. Okay. Next I will again visit the next this visitor vector. Where I will see that okay this is still false. So this will create a new component because this is not the part of the previous component, right? So again I will start a visitor from here, and I will actually check all the adjacent of this current node, and it will be part of the next component 1. Got it? In this I can actually count how many actually components actually I have. You can also solve this problem if you not yet solved this problem. This is a problem that count the number of components. Okay, so what will be the edges for the modified graph? It will be added if the time of the edge is greater than t, whatever the t actually we are trying to consider. Okay, then actually we will check what is the number of components. Suppose for this example, yes, this is the problem. I think count number of complete components. You can solve this problem first. Then it will be easy to understand that how can actually count this component. So here actually you can see this example. Like you can in the image from actually you can see that this actually one unique component this 3 actually part of one other or another component, and this 3 node 3 and 4 actually part of another component, right? So how many actually components are here? Actually 3. So that's why actually output is 3. Okay, so from this image, how many actually components are there? 2, because these 3 actually part of one component, these 3 actually part of the one component, correct? But this actually they are trying to different condition, that how many actually complete. So complete means another condition actually they have added, but the problem statement is the same, that we have to count the number of components here. Okay, got it? So now, so we from that actually we can count the number of components from the modified graph. I will create the first modified graph. We only add the edges that actually time is greater than t. Alright, then actually check how many components I actually have. So what are the time study for that? So t can go up to big of t, because t can start from 0 and it can go up to 10 to the power 9, and after that I am checking how many components I can actually create from this at the time t. So for that, what I have to do, I have to iterate all the edges to check that this actually edge is part of the it can be part of the current graph or not, right, at the current time. So that's why I have to traverse all the edges. Then what I have to do, I will actually traverse all the actually what is, because suppose there are n nodes, so at least I have to visit all the nodes at least once, or also at most once, because I have to visit only once, right? Otherwise visitor will be true, so I will not visit them again. So that's why all the nodes will be visited once. So that's why for that, to check the how many components I can actually create, first I actually do visit that all the edges that actually I have to check that this is actually part of the current graph or not. So that's why it will take big of e number of edges, and then actually I have to visit all the edges, all the nodes or all the vertices of the graph to visit that in which component it is part of that, right? And that's why it will take actually big of e plus v. Now it will actually run how many times? It will run actually t times, right? So it will almost take n square t into e plus v. This is clear why it will give us t into e plus v, because I will first what I will do, I will check for t is equal to 0, then again I will traverse all the edges, then actually I will traverse all the vertices of that. Next again for t is equal to 1, I will traverse all the edges to consider only those edges that actually time is greater than the t, right? And again I have to traverse all the vertices. So that's why it will multiply with t into e plus v, correct? And here so t is equal to 10 to the power 9. So in the worst case, it will actually give us TL. Clear? Now how can I actually optimize this here? So optimize approach. So somehow I have to find the minimum time, right? Minimum time. So if this actually always constant, right? We can't actually optimize that to count the number of components in a graph, right? This is actually constant. But we can actually optimize this in this time t. Actually, I'll just multiply with t, but we can actually optimize how. So if I use the binary search here, so what is binary search? I know that our time will be between 0 to 10 to the power 9. So I will take two pointer, L is equal to 0, H is equal to 10 to the power 9. I will get one mid pointer, that will be L plus H by 2. So this mid will be ultimately our t. So I will check that with this mid, this time mid, how many actually components I can create, right? So that actually I will actually suppose this helper function, or actually pass the edges and the time we are trying to consider, that will be mid, right? So I will get one count, how many components. If count is greater than equals to k, then what I have to do, I have to minimize that, because this is one possible answer. So answer will be one this time. This mid is one possible answer, right? Because by using this time t is equal to mid, I can create at least k number of components, right? But whatever target, our target is to minimize the time. So then what have to try? The next our target is try to shift the right pointer to the mid minus 1. So that means suppose initially our this actually L, this actually H. Suppose now by using this mid, I got a valid answer. That means this by using t is equal to mid, I can actually create at least k number of components, right? Now this is one possible answer. Okay, that's great. But our ultimate target is to minimize the t. So this will be always our answer, one possible answer. This is possible answer, but this is actually optimal. The minimum time, no, because this is still a minimum time. So I do not need to search this here in this region, correct? So that's why I will shift the right pointer h to mid -1. Clear? Why actually I'm shifting the right pointer or the h pointer in the mid -1? Clear? Because I have already found one best answer as mid, but our next goal is to get more minimum time. So that's why I will shift the right pointer to the mid -1, because it can actually give me better result, right? So that's why next our search scope will be here, right? So that's why you have to like t is equal to 0, 1, 2, 3, 5, actually 10 to the power 9. So suppose in mid is equal to 5, I got one possible answer. So our next target is it possible to with t is equal to 2, right? That will be our target. So that's why if our count is greater than equals to k, then this is one possible answer. I'll consider that. And next our target will be more minimum time. So that's why I'll shift the right pointer h to mid -1. Else this is not possible. Suppose at t is equal to mid. So our next time will to increase the time. So that will be else will be mid +1. Why am that time actually shifting the left pointer to the mid +1? Suppose this is our example. T is equal to 0, 1, 2, 5, actually 10, suppose 10 to the power 9. By using this mid, I am not able to generate k number of components. That means we have to consider more edges, because that means we actually have one actually to be removed. Suppose this is two component here actually initially. Okay, suppose t is equal to 1, it will be removed. T is equal to 2, it will be removed. 3, it will be removed. 4, it will be removed. At the time 5, it will be removed. Now at t is equal to 3, I want to check how many components I can actually create. So that means the graph will be, so t is equal to 3. So this edge will be not present. This edge will be not present. This 2 will be not present. This edge also not present. This edge also be not present. So this edge also be present. This is also be present. So this will be present. These two edges. Correct. Now how many actually components actually I have in this graph? That actually component number 1, 2. This will be part of only one component, and 4. So here actually I can actually create 4 components. But our target is k is equal to suppose 5. So what actually I have to know? What actually I have to do actually? Ultimately what I tried. So I have to create more number of components. Then how actually to create more components if there is no edge, right? So that's our target is to reach the time. So to increase the time, then what will happen? That one, it may possible that some edges can be removed. So suppose in the t is equal to 5. So here is the t is equal to 3. Suppose t is equal to 4. I want to create a graph. So what will happen? Let's see the graph. So the nodes actually this. So at t is equal to 1, it will not be part of that. T is equal to 2, it will not be part of that, because our t is equal to 4, and our k is equal to, our target is to create 5 number of components. So this t is equal to 3, it will not be part of the current graph, this edge, and 4, this will be not a part of the current graph because our current time is 4, so it will be removed. And this edge only be present between these two nodes, right? That is removed at t is equal to 5. So this edge will be only present. Now how many components are actually I have? 1, 2, 3, 4, 5. Got it? So honestly I increase the time, more number, it may actually remove more number of edges, correct? And that actually lead us to get more number of actually components. It may actually create more number of components, right? So that's why our target is if our current components I can create at the time mid. Suppose I got someone mid. So from binary search, suppose I got one mid. So this is our mid. So by using this mid, I got actually less than k number of components. Now our target is to create greater than equals to k. So how do I have to check with this time? It may actually create, because this is the greater time than greater than mid, so it will actually remove more, it may actually remove more number of edges. So that's why I will actually shift the left pointer to the right side. Got it? If our current number of components actually less than k, because I've already explained in the by drawing the actual graph also that it may actually remove more number of edges, because I have already removed all the edges that will be actually less than equal to mid, right? Still actually we got actually less than k number of components. So next, how next like get the more number of components, our target is to get at least k. So that will be, we will only get if we remove more number of edges, and that actually will be possible if we actually increase the t, right? So that's why that time I will shift the right side. Got it? And that will be mid plus 1. So actually you can see, yes, if or else, that means count is less than k, so that time shift the left pointer to the mid plus 1, because I have already checked mid, we don't need to check mid again, and I have to go to the right side of this mid, right? I have already explained why. So how actually optimize this? So I have used the binary search here, and everything else is same. So how little time to it will take to by using the binary search? So it will take actually log n, right? Binary search actually takes log n, so that's why it will be log of t into e plus b. Got it? How can you optimize this? So now what is the code? And if you found this the logic clear, so please subscribe channel and also like the video. Now go to the code. So first of all, I will create a new edges. Okay, new edges vector. Or actually I will just change the order. Like first I will store the time, and then actually the u and v. In the input array, it actually the order is ui, vi, and time I. But in the modified edges, actually what have you done? First store the time, it will be removed, and the u and v. Got it? So just iterated the input edges, and I have created the new edges. Okay. Now I have sorted these new edges. How? In the descending order, because I know that the if I actually sorted in the descending order, then what will happen? The edges that is present at the front, that will be part of the current graph. That means I have stored in this way that 10 ui vi, then 9 ui vi, okay, then 8 uj vj. So I have sorted in this ascending order of the time with respect to the time. Now, so what will happen? That suppose I want to know that t is equal to 9, at t is equal to 9, how which edges will be part of the current graph. So I can actually go to this left to right and easily check that okay, this current time 10 is greater than equals to 9 or t. So it will be part of the current graph. If any of this actually, if any time suppose it will fail at the this edge, so I can actually break from here, because I don't need to check the next edges, right? Because that will be always greater than equals less than equal to the current time, right? So that's why it will be easy to more optimal. So that's why I've sorted in this order of the descending order of the time. Now what I have to do? I have to use the binary search. So I will take two pointer. One is the left pointer and the right pointer. Left pointer it can start with 0 and it can go up to 10 to the power 9. Here I will use 10 to the power 9 plus 7. All actually okay actually. So I have to return the answer, right? So initially it is -1. So I have initially -1 to know that I have found any answer or not. Okay. So till honestly you have to run the binary search. So till our actually L less than equal to H. So left pointer is less than equal to H. So that means we have to still have some search space. Otherwise, if left is greater than right or H, that means we have already crossed the search space, right? So I will check. I will get one mid L plus H by 2. So by using, so this is your current T mid. So by using this mid, I will check that how many actual components I can create. So this helper function will return that how many actual components I can create by in this time mid, T is equal to mid. So I actually passed new edges, the modified edges, and the number of actually nodes actually I have, and the current time on actually I want to create. I want to know that how many actually components I can create. So it will get some components count. So I'll check that the count is greater than equals to k. That means this is one possible answer. So I'll store that answer is equal to mid. Okay. Else, and also what to do? I have to try to search the minimum time again. So that's why I'll shift the right pointer h to the mid minus 1, because it may in the left side it may actually in the future it can actually give us the more minimum time, right? So that's why I'll shift the right pointer h to the mid minus 1. Else this is not possible to generate at least k number of components. So that time I have to increase the time. So that's why, because if increase the time, so I can actually get more number of components, because it may actually remove more number of edges at the time. So it can actually create more number of components. Components mean these are disconnected, right? These two nodes are disconnected. So that's why I'll increase the left pointer, shift the left pointer to the mid plus 1. Got it? And ultimately return the answer what actually I will find the minimum time. Okay. So helper function what actually do? It will check the number of components. So I'll first create the adjacent list of the n nodes. So I'll iterate the new edges from left to right. I've already sorted in the descending order. So I'll check that the current time it will be removed is it greater than t. So that will then the current edge will be part of the current graph. So that time I will add this current edge. So it is actually undirected graph. So u cross u, I can go from u to v, and also I can go from v to u. So that's why I'll store both the things. From at the list of u, I'll store the v, and the list of v, I'll store the u. Else I'll break, because I have already sorted in the order of the time, right? If any of the fails, so I can also break from that. Now what I have to do? I have to count the number of components. So to count the number of components, what we need? We need one visitor vector that actually indicate that this node actually already visited or not. So that's why I have taken one visitor vector n of order change is false. That means none of this is visited yet, and the number of components I can actually create it till now. So I can just start this undirected graph. I can start from anywhere. So that's why I'm just iterating from 0 to n. Okay. So I'll check that the current node is still false. That means we have not visited the current node. So I can visit. So I'll start visiting. From here the current node I, and I'll pass the adjacent list and also the visitor vector, because whatever node actually visited in the current hierarchy, so I have to mark that as also that's visited, right? So that's why I'll pass these two things, and also increase the number of components, because this is actually one component. This will create one component, right? So ultimately after this for loop, it will actually check this component variable will return that how many actually components I have created, right? So this DFS function what will do, it will just visit all the adjacent or all the nodes we can visit from the current node. So first of all, mark this current node u to true, because it is visited now, and I will now check the adjacent nodes for the current node u. So I'll see that have I visited this current adjacent node v. So if it is still false, then actually I will only visit, right? Otherwise I will not visit of that. So this actually is a simple DFS to visit all the nodes actually part of the current hierarchy. I can actually visit in the current node from the current node. So this is unrated, so there is no problem. So I will actually visit all the nodes in the current component. So this is actually one component, right? So after that I will increase the component, and next I will go to suppose next node 1. So I'll check that it is still false. If it is still false, that means this is creating another component, right? Suppose this is suppose 0, 1, 2, 3, 4. Suppose I started, I'm checking the visitor vector from 0 to 4. So I'll check this, okay, this is false. So I'll start visiting from node 0. So I'll mark this as true. Again, I'll go to the adjacent node of 0. It will be come to 1. So I will again visit the adjacent node of node 1. So I will go to the 2. So I will mark this as true. Now I have completed this hierarchy, right? Next, so this is actually component number 1. Next, I'll check 0. Okay, this is 0 already true. Now 0, 1, this is already true. That means I have already visited in some component. It may create another component also. And now node 2, this is now visited all true. That means we have visited this one. Next is 3. This is still false. So this will create another component. So which node actually part of this current component? So 3 will be part of current component. So it will mark as true. Next adjacent node of 3, it will be 4. So I'll mark this as true. So this is actually component number 2. Got it? ultimately after that I will check that node 4 is still false. No, this is true. So this is part of some component. So I'll go to the next is 5. So I do not have anything, so I'll break from here. So how many component I've created here? 2. Got it? So this is clear. So if you found this video useful, please like the video, and if not subscribe, please subscribe the channel. Thank you. Bye.